All right, what is up, you guys? Welcome back to another differential geometry stream. I'm Anthony, and I'm going to avoid a 16-minute unscripted rant right off the bat in the beginning of this. I'm going to get to reading the book ASAP, but I wanted to do something a little bit different. This is the third take. Never done this before. This is obviously a fresh one. I'm peeling off the plastic. Here we go. Nope, it's not for you. It's not for you. This is not for cats. Please. Woo! Okay, here we go. Yeah. And I'm gonna do a quick little... Whoa! Yowza! This is a horrible solve. Oh wow, the timer did not even start. I'm gonna try out these smelling salts here for you. I don't know if it's gonna focus this time or not. Did the first two takes on camera. My cat got in the way first, and then the timer here didn't work because I'm gonna do a Rubik's Cube solve casually right after a third whiff of the salts here. Here we go. Okay. Do a little scramble here. And let's get this. It's a suboptimal angle, but we're cubing and then reading the book. So, you know, got to make compromises. Let's do a little quick inspection here. Okay. Wow, my fingers are really tensing up. So I don't know, not bad. We have a 16.15. You can see the time on the screen, hopefully, if I got the editing down, but just a little quick casual Rubik's Cube solve to start things off. Okay, but on a little bit more of a serious note, I'm going to read some, well, a viewer comment from last time that I thought was good. This is from Vander Hagen the Stampede. And they say, so, in the context of differential geometry, contact involves a deeper geometric relationship between two geometric objects at the points where they intersect. As this concept emphasizes the idea of higher order coincidence or alignment of derivatives, using the term osculation could help convey a more precise description, but that is just an opinion. And you know what? On my channel here in the differential geometry stream comments, I appreciate that opinion. That opinion is welcome. I think if you guys want to hash it out in the comments on what terminology conventions we should adhere to, I am a big supporter of that because, I mean, what is the point of terminology in the first place? It's so that other people can understand the geometric concepts that you've got going on in your head or that you're visualizing, drawing, whatever. So the conventions are important, and making sure that we're all adhering to them, that just fosters greater community, in my opinion. So thank you, Vander Hagen the Stampede, for your comment. And without any further ado, we are going to get into reading Differential Geometry by Erwin Kreyszig. Now this is at the tail end now of chapter 2. These are the last two sections. We're going to go over Involutes and Evolutes and Bertrand Curves. There's, I think, in my pre-read that I did, there's about 4 proofs that we're going to go over today, which are both in the bodies of the text as well as in the problems, which I'm going to read the solutions for. The solutions being proofs. The problem is just prove a theorem. The solution is just the proof itself. So, section 22. Involutes and Evolutes. Involutes and evolutes are curves associated with a curve in the following manner. In general, the tangents to a curve vector x of s, where s, of course, represents the arc length of the curve, generate a surface called the tangent surface of this curve. For detailed investigation of this surface, see section 58, which is in chapter 6, which goes into mappings, and that specific section is called ruled surfaces or developable surfaces, which who knows when I'm going to get to that, but I'm going to get to it eventually in one of these. In consequence of the representation 10.3 of the tangent, which that's just vector y of real parameter u is equal to vector x plus parameter u times vector t, where the vectors x and t depend on the curve capital C proper and the particular point that you want to define this tangent about. We obtain immediately the following representation of the corresponding tangent surface, which is given by y in terms of parameter s for arc length and parameter u, which is also just a real parameter, equals vector x of s plus real parameter u times vector t of s, where s denotes the arc length of the curve and u is a real parameter whose absolute value equals the distance of a point capital P of the surface from the point P naught of contact of the corresponding tangent with the curve. U is positive if the directed segment P naught P has the same sense as T and is negative otherwise. The angle gamma, which is greater than or equal to 0 and less than or equal to pi, between two intersecting curves is defined as the angle between the unit tangent vectors to these curves at the intersection point. We consider a curve, capital C proper, given by its vector parametric representation x of s of class r greater than or equal to 2, that is to say it is at least twice differentiable, with non-vanishing curvature kappa of s. Since any involute of the curve capital C lies on the corresponding tangent surface, we can represent it in the form vector z of s equals x of s plus function u of s times vector t of s, where the function u of s denotes an r minus 1 times continuously differentiable function to be determined so that the above orthogonality condition is satisfied. According to this representation, the unit tangent vector to the involute is z dot, or the derivative in terms of arc length of the vector z, is equal to the vector t plus dds of real parameter u times vector t, which is equal to vector t plus real parameter u times curvature kappa times the unit principal normal vector p plus the derivative in terms of arc length of u, or u dot, times the vector t. In consequence of the orthogonality, z dot scalar product with the vector t, or you could say z dot dot product with the vector t, is equal to 0. So in consequence of the orthogonality, that must hold. Therefore, 1 plus u dot equals 0, or the function u of s is equal to c minus s, where c is a constant. From this, we obtain the following representation of the involutes of the curve vector x of s. So the involutes are given by this representation. Z of s, which is a vector, is equal to vector x of s plus the quantity c minus s, then times the vector t of s. Every real value of c corresponds to exactly one of these infinitely many involutes of the given curve capital C proper. Since kappa is greater than 0, not equal to 0, because we can't have vanishing curvature, then we have that z dot is non-zero for all values of s not equal to that constant c. So the derivative of the vector z in terms of arc length is non-zero for all values that the constant is not equal to the arc length at which we're defining this involute about. If capital C proper is a plane curve, its tangent surface is a plane which coincides with the plane of the curve. In this case, the involutes are therefore plane curves, not osculating curves, plane curves, or not osculating planes with curves, plane curves. Anyways, so we may interpret the formula representing involutes in the following manner. If a thread lying on a curve is wound off so that the unwound portion of it is always held taut in the direction of the tangent to the curve, while the rest of it lies on the curve, then every point of the thread generates an involute of the curve during this motion of unwinding a thread. Previously, we started from a given curve and determined its involutes, and this is shown in figure 28 here. Let us now treat the converse problem. Let a curve capital C be given and determine a curve C star so that the given curve is an involute of C star. The curve C star is then called an evolute of C. And here we have a historical note here, the first of a couple that we're going to have. The names involute and evolute were introduced by Christiaan Huygens, who lived from 1629 to 1695. In 1665, in a work called Horologium Oscillatorium, Part 3, which was actually published, I guess, in 1673. Historical note about Christiaan Huygens: if you paid attention to any of my rants in the previous couple of streams and you didn't skip them, thank you. You're one of the hardcore members of the audience. But Christiaan Huygens was more or less a contemporary of Newton, but they had differing theories of light. Huygens was, I guess, the originator of the wave theory of light, whereas Newton was the progenitor of the corpuscular model of light, a particle model of light. So focusing on what we would now call photons, but Newton didn't call them photons or conceive of them as packets of wave energy of light. He was just, billiard balls model of the universe. Everything's a billiard ball, mass, light, everything, and that's where his framework jumped off from. But Christiaan Huygens, a Dutch individual, if I'm not mistaken, he originated the wave theory, but his theory was not as popular as Newton's, and so it was kind of forgotten until later. As I kind of mentioned, we had Jean-Augustin Fresnel and Cauchy, and they basically brought the body of knowledge of science up to a critical mass where then the wave theory of light would kind of be redeemed hundreds of years after Christiaan Huygens originally came up with it. But all this stuff about involutes and evolutes comes from another project of Christiaan Huygens, which is that this guy was a master of pendulums. Christiaan Huygens, I guess his work contains the first idealization of a physical problem by a set of mathematical parameters, and he was the first to provide a mathematical and mechanistic explanation of an unobservable physical phenomena, namely gravity in pendulums. And actually, he was so precise about it that he invented the pendulum clock, which for another 300 years after that would be the most precise form of timekeeping. We get his wave theory of light from a treatise called Traité de la Lumière. But like I said, it's his horological research. That's horological with an H and not to be confused with the research that I do on dating apps. But his horological research into clocks, that's where he coined the terms involutes and evolutes. So, of course, I like to pull up these guys' Wikipedia pages every now and then, and we can see here, his theory of light was initially rejected in favor of Newton's corpuscular theory of light until Augustin Jean Fresnel adapted Huygens' principle to give a complete explanation of the rectilinear propagation and diffraction effects of light in 1821. And so, yeah. Moving right along, We will now find a representation given by the vector y of s of the evolutes c star of the curve C given by its vector parametric representation x of s, assuming that the curve C is of class r greater than or equal to 3, that is to say it is at least 3 times differentiable and has non-vanishing curvature kappa of s. By the definition of an involute, the tangents to C star must intersect the given curve C orthogonally. An evolute may consequently be represented in the form vector y of s equals vector x of s plus function q of s times vector a of s, where vector a of s is a unit vector in the normal plane corresponding to a point x of s of the curve, and obviously the magnitude of q of s is then the distance between that point x of s and the corresponding point y of s of the evolute. In consequence of the definition of the involute, the vector A must be tangent to the curve y of s. Therefore, the derivative of the vector y in terms of arc length, or y dot, is equal to dy ds, which is equal to beta times the vector A, where beta is a scalar. Using the preceding representation, we obtain from this the condition the vector t plus q dot times the vector A plus q times A dot equals beta times A. Since the scalar product of the vector A with itself, or A dot A, is equal to 1, and therefore A scalar product with its derivative with respect to arc length, so A scalar product with A dot equals 0, and also t scalar product with A, or t dot A, is equal to 0, we thus find that q dot equals beta. So the derivative in terms of arc length of this q is equal to beta, the scalar. Consequently, vector t plus q times A dot being of course a derivative in terms of arc length, this is equal to 0. Now the vector A lies in the normal plane and is therefore of the form A equals principal normal vector P times sine of alpha plus B, which is a unit binormal vector, times cosine of alpha, where alpha denotes the angle between the vector A and the unit binormal vector B in terms of arc length S to the curve C, which is shown in figure 29 right here. Differentiating this representation with respect to S, inserting it into the foregoing equation, and using, it says 15.1 here, but those are the formulae of Frenet, we find that vector t plus q times, this is a very large outer quantity, but then we have a smaller inner quantity, which is given by negative kappa times vector t plus tau, representing torsion, times b, closed quantity, the inner smaller quantity that is, times sine of alpha plus alpha dot times vector p times cosine of alpha minus tau times vector p times cosine of alpha minus alpha dot times vector b times sine of alpha, close the entire larger outer quantity. This is equal to 0. Now, since the tangent, the unit principal normal, and the binormal vector t, p, and b are linearly independent vectors, the coefficient of each of these vectors must vanish. We thus obtain 1 minus kappa times q times sine of alpha is equal to 0, or q times sine of alpha is equal to rho, the reciprocal of curvature. And furthermore, quantity alpha dot minus tau closed quantity times cosine of alpha is equal to 0, as well as we have quantity tau minus alpha dot closed quantity times sine alpha equals 0. Now, since for any value of alpha, at least one of the functions cosine of alpha and sine of alpha is different from 0, then by those two expressions, alpha dot equals tau must hold. And integrating this relation, we have that alpha of s is equal to the integral from 0 to s of tau in terms of sigma, d sigma, which sigma is just an integrating variable here. And this integral is then plus k star, where k star is a constant of integration. By means of these conditions, we obtain the desired representation of an evolute of the curve C, given by its vector parametric representation x of arc length s, in the form vector y of s equals x of s plus rho of s times the quantity vector p of s plus b of s times cotangent of alpha of s, closed quantity, as well as we have that alpha of s is equal to the integral from 0 to s of tau of sigma d sigma plus k star, where, of course, vectors p of s and b of s are the unit principal and unit binormal vectors, respectively, to the curve capital C. Each value of the constant k star corresponds to exactly one of the infinitely many evolutes of the curve C. Now, comparing the formulation for evolutes, and we, in an earlier section, section 19, we were given this vector A equals vector x plus rho, the radius of curvature, times the vector p, which is the unit principal normal, plus beta times the unit binormal vector. This vector A gives you a representation of what's called the polar axis of the curve C at the point P that you're defining these tangents about, but it also passes through the center of the osculating sphere about that same tangent point on the curve. So comparing the equation that we just obtained for the evolutes and this equation for the polar axis of the curve at the point, we see that any point y of s of any evolute lies on this polar axis of the curve at the corresponding point. Furthermore, we stress the following simple property of the evolutes, which is an immediate consequence of the representation of an evolute. All right, Theorem 22.1. Let y superscript quantity 1 of s and let y superscript quantity 2 of s be two different evolutes of the same curve vector x of s. Then the angle of intersection of the tangents to y superscript quantity 1 and y superscript quantity 2 corresponding to any value of s is the same for all values of s. We have a few remarks, and then we're going to be proving this as the sole problem for section 22. If a curve is plane, so it's not an osculating plane we're talking about, but this curve is completely incident in the plane. If a curve is plane, tau equals 0, then in the representation for evolutes, the angle alpha is constant. Plane curves have only one plane evolute. This evolute corresponds to the value k star equals pi over 2 and lies in the plane of the curve, is the locus of the centers of curvature of the curve. The other evolutes are general helices on the cylinder, which is orthogonal to the plane of the curve and intersects it along the aforementioned plane evolute. So now we're going to go to prove Theorem 22.1, and like I said, my PDF here is missing these critical pages. This is actually probably one of, if not the shortest proof in this book. Two different evolutes of the same curve correspond to different values of alpha of s. Since alpha of s is the angle between the vector A and the unit binormal B, the statement follows. There you have it. Moving right along, section 23, Bertrand curves. Bertrand. Two curves which at any of their points have a common principal normal are called Bertrand curves, as per Joseph Louis Francois Bertrand. I think between Monsieur Bertrand and Riemann, those two guys are kind of viewed as like the big pillars of differential geometry, if I'm not mistaken. Especially Riemann, obviously, but I think Bertrand also gets some credit in there for being one of the big heavy lifters in differential geometry. But example 1. If capital C is a plane curve, we can always find a curve C star such that C and C star are Bertrand curves. Indeed, if capital E is the plane evolute of C, then all involutes C star of E have the same principal normal as the given curve C, because by definition of the involute, these curves intersect orthogonally any tangent to E, which is shown in figure 30. C and any of the curves C star are therefore Bertrand curves. Moreover, it follows from the representation of the involutes of a given curve that the distance measured along the common principal normal between corresponding points of any two of these involutes is constant. Two plane curves are therefore called plane parallel curves if they have common principal normals. And this name was introduced by Gottfried Wilhelm Leibniz, which we all know him for coming up with the better notation for derivatives, if I'm being perfectly honest, because all of these fly dot derivatives for representing derivatives in terms of arc length, that's all Newton's idea, okay? Leibniz was all about using primes and d, dx, dds, ddy, using the d differential infinitesimal notation. Way better. Just saying. Example 2. The principal normals to a circular helix C, our beloved circular helix. We've seen this in a few streams now. Example problem 12.2, we basically already went over deriving representations, expressions for involutes and evolutes of our beloved circular helix. So the principal normals to a circular helix C intersect the axis of rotation of the cylinder Z, on which C lies at right angles. The points of intersection of these normals with any cylinder Z star coaxial with Z determines a circular helix C star as shown in figure 31. Obviously, C and C star are Bertrand curves, and there exist infinitely many helices C star of this type which, together with C, are Bertrand curves. If two curves C proper, which is given by the vector parametric representation x of t, which has positive non-zero curvature, kappa, and a second curve C star, which has a vector parametric representation given by x star of t. So two curves, C and C star, but they're not given in terms of arc length this time for once. These curves are Bertrand curves then by definition, and C star can be represented in the form vector x star of t is equal to vector x of t plus a of t times vector p of t, where vector p of t is the unit principal normal vector to C, and the scalar a of t is the directed distance of a point p star of C star from the corresponding point P of C. A of t has a positive sign if the sense from P to P star is that of vector P of t, the unit principal normal vector, and a negative sign otherwise. We will prove shortly that A is a constant, that is independent of parameter t. While for every plane curve C, there exists a curve C star so that C and C star are Bertrand curves, this property does not hold in general for twisted curves. And now we have Theorem 23.1, which will be proved immediately after. Theorem 23.1, for a given curve C, there exists a curve C star so that C and C star are Bertrand curves if and only if the curvature kappa and the torsion tau of C satisfy a linear relation with constant coefficients, namely C1 times kappa of t plus C2 times tau of t equals 1. And now on to the proof. Part 1. we assume that the curve C given by vector parametric representation x of t and curve C star given by its respective vector parametric representation x star of t are Bertrand curves. So the assumption in this leg of the proof is that C and C star are known to be Bertrand curves. And then as a little bit of a hint, we're going to go from that definition to derive the relation C1 kappa of t plus C2 tau of t equals 1. We denote by S and S star the arc length of C and C star respectively. So starting from the definition for, or I guess just the formulaic representation of involutes, we will first prove that A is a constant. Since A is the directed distance of corresponding points of C and C star, A is a constant if and only if the following relation, which is d dt of A squared, or the derivative in terms of t of A squared, equals d dt of the larger quantity, smaller quantity, x star minus x, closed quantity, dot product with another smaller quantity, x star minus x, closed smaller quantity, closed larger quantity. So this is then equal to 2 times the scalar product between x star minus x and x star prime minus x prime. Hopefully that wasn't too hard to listen to. So this whole entire expression, which was originally from the derivative in terms of t of A squared, it then vanishes. And so A is a constant if and only if that quantity for the derivative of A squared in terms of t vanishes. But this is true since the vector which represents the difference between x star and x, so the vector x star minus x, this is true since that vector lies in the common principal normal, while the vectors x star prime and x prime, okay, when we use primes, those are derivatives not in terms of arc length, but just of a linear real parameter t. So those vectors x star prime and x prime are tangent to C star and C respectively, that is, they are orthogonal to that principal normal. We denote by t and t star respectively the unit tangent vectors to C and C star. We have the following expression, d dt of t star scalar product with t is equal to t star prime scalar product with t plus t star scalar product with t prime. This expression vanishes since the vectors t star prime and t prime lie in the common principal normal. Denoting by alpha the angle between the tangents at corresponding points, we thus have that the scalar product of t star and t is equal to cosine alpha, which is equal to a constant. This is just simply due to the definition of the dot product or scalar product. That is, at all points of C and C star, the angle between the tangents is the same. Instead of the arbitrary parameter t, we introduce now the arc length s of C as parameter, writing the expression for the formula of the Bertrand curve of a given curve in the form x star of s is equal to x of s plus a times p of s. Then cosine of alpha is equal to the scalar product of t star and t, which is then equal to dx star ds times ds ds star scalar product with the vector t, which is equal to ds ds star times the quantity vector t plus a times p dot, derivative in terms of arc length of p, closed quantity scalar product with t. And this is then equal to ds ds star times the quantity 1 minus a times kappa, which is a constant, and we have that the magnitude of the cross product between t star and t is equal to the magnitude of ds star times the large outer quantity vector t plus a times smaller inner quantity negative kappa times vector t plus tau times vector b, closed quantity, smaller inner closed quantity, cross product with the vector t, and then we close the outer quantity. This is then equal to the magnitude of ds star times a times tau times vector p. From this, in consequence of the definition for cross products, as well as from what we had previously described above, t star dot product with t equals cosine alpha equals constant, as well as from the fact that the magnitude of the unit principal normal is 1 because it's a unit vector, it follows that a times tau times ds d star is equal to plus or minus sine of alpha, which is constant. And from what we had just derived for cosine of alpha and sine of alpha, we obtain a numerator 1 minus a times kappa over denominator a times tau is equal to c, which is equal to a constant. So setting a equal to c1 and c equal to c2 over a, then this 1 minus a times kappa over a times tau equals c. This becomes identical with the c1 kappa plus c2 tau equals 1 relation, which is what we want when we go from Bertrand curves implies, that's what we want. And that concludes the first leg of the proof. Now, we are going to go to the second part of the proof, which is going in the reverse direction, because keep in mind, this is an if and only if theorem. So we have if implies this way, and then only if going in the other way. We're proving the opposite direction. Part B, here we go. The condition c times kappa plus c2 times tau equals 1 is also sufficient. We start from a curve, capital C proper, given by its vector parametric representation x of s with the arc length s, and introduce a curve C star, which is given by x star of s equals x of s, which is a vector, not s, but x is a vector, plus c1 times vector p of s. And prove that if the c times kappa plus c times tau equals 1 is satisfied, then that implies that c and c star are Bertrand curves. So differentiating the vector parametric representation of the curve c star, given by the vector x star, with respect to s and making use of the formulae of Frenet, we find that dds of x star is equal to vector unit tangent t plus scalar c1 times the derivative in terms of arc length of the unit principal normal p, which this is then equal to the quantity 1 minus c1 times kappa closed quantity times the vector t plus c1 times tau times the vector b. This vector is tangent to c star. If we write c1 times kappa of s plus c2 times tau of s equals 1 in the form 1 minus c1 times kappa equals c times c1 tau, and c is equal to the ratio of c2 to c1, or c is equal to c2 over c1, and insert this into our derivative for the vector parametric representation of the curve c star, we obtain dds of x star is equal to c1 times tau times the quantity c times vector t plus vector b, closed quantity. Hence, if the orientation of c star has been suitably chosen, the unit tangent vector to curve c star is of the form t star is equal to numerator scalar c times vector t plus vector b over denominator, which is scalar square root of the quantity 1 plus c squared closed quantity. From this, by the formulae of Frenet, we have that dds of t star is equal to 1 over the square root of the quantity 1 plus c squared, and this is then times the quantity c times kappa minus tau, closed quantity, times the unit principal normal vector p. Since this vector is the derivative of the tangent vector to c star, it lies in the principal normal to c star, and this normal coincides therefore with that of c. Hence, c and c star are Bertrand curves, and this completes the proof. Now, it follows from this proof that we can write the relation c1 times kappa plus c2 times tau equals 1 of the form, or in the form rather, kappa plus tau times cotangent of alpha equals 1 over a. And alpha cannot be 0 here, where a has the above meaning and alpha is the angle between the tangents at corresponding points. And we have to exclude the trivial case alpha equals 0, which corresponds to plane or coinciding curves. From Theorem 23.1, we obtain the following interesting fact, which is Theorem 23.2. A circular helix C is the only twisted curve for which more than one curve C star exists, such that C and C star are Bertrand curves. And we have a nice quick easy proof here. If for a given twisted curve C, there are two curves, say C star represented by x star of t equals x of t plus a of t times vector p of t, and C double star represented similarly by x double star of t equals x of t plus a double star times p of t, where a double star does not equal a, so that C and C star as well as C and C double star are Bertrand curves, then C must satisfy, in addition to the relation kappa plus tau times cotangent of alpha equals 1 over a, another relation of the same type, kappa plus tau times cotangent of alpha double star equals 1 over a double star, where alpha double star is non-zero. From both the relations, we see that both the curvature kappa and the torsion tau of C must be constant. Since the natural equations determine a curve up to its position in space, and since circular helices have constant curvature and torsion, the curve capital C is a circular helix. Furthermore, we see that there are infinitely many curves, which must also be circular helices, so that C and any of these curves are Bertrand curves. In the case of curves of constant curvature, the following fact holds. Theorem 23.3. For a given twisted curve C of constant curvature, kappa equals kappa naught, which is greater than and not equal to 0, there always exists a curve C star such that C and C star are Bertrand curves. If in particular C is not a circular helix, C star is a twisted curve of the same constant curvature, kappa star equals kappa naught. Then each of these two curves is the locus of the centers of curvature of the other, which we saw that when I was in reading section 12. At corresponding points, P and P star, the unit tangent vectors to these curves, are orthogonal. The normal plane of C at P coincides with the osculating plane of C star at P star. This is proved as follows. If not only the curvature but also the torsion is constant, capital C, the curve proper, is a circular helix. This particular case has already been considered. We may therefore assume that tau is not constant. Then the relation kappa plus tau times cotangent of alpha equals the reciprocal of A takes the form kappa naught plus tau times cotangent of alpha equals 1 over A, where tau is not constant and alpha is non-zero. So the only solution of this equation is that kappa naught equals 1 over A and cotangent of alpha equals 0. And So at corresponding points, the tangents to both curves are orthogonal. Since the curves have in addition a common principal normal, the statement about the osculating and normal planes follows. Since A equals the reciprocal of kappa naught, or A equals 1 over kappa naught, which is equal to rho naught, or the radius of curvature is given by the definition of the reciprocal of curvature, in consequence of the formula for the Bertrand curve of a given curve, then C star is the locus of the centers of curvature of capital C proper, which again you can see details of that in section 12. If one of two Bertrand curves is plane, the other must also be plane. So if one of these Bertrand curves is a plane curve, then the Bertrand curve to that initially given defined curve is also going to be a plane curve. Therefore, in our case, C star must be a twisted curve. That is, the torsion of C star, tau star, is not equivalent to 0. It is non-vanishing. So C star must thus satisfy the relation kappa star plus tau star times cotangent of alpha star equals 1 over A star, where alpha star is non-zero. And this is given by the relation kappa plus tau times cotangent of alpha equals 1 over A. From this, we have that the vector x equals vector x star plus A star times vector p star, and vector p star is equal to plus or minus the vector p. And so by the formula for the Bertrand curve of a given curve, we obtain the relations that the magnitude of A star is equal to A is equal to rho naught, and alpha star equals pi over 2. Therefore, kappa star equals kappa naught, and C is the locus of the centers of curvature of C star. And now we have our third rapid fire proof, basically. We mentioned finally the following interesting property. The product of the torsions of Bertrand curves is constant. This is proven in problem 23.1. It's kind of a little bit circular here. So, problem 23.1, the proof of theorem 23.4. Since the unit tangent vectors t and t star are orthogonal to the common principal normal to the curves, t star is of the form t star equals plus or minus the quantity of vector t times cosine of alpha plus vector b times sine of alpha, where alpha is the constant angle between t and t star. If we take the vector product of this relation for t star and p star, we have that the binormal vector b star is given by the cross product of t star with p star, which is equal to the quantity vector t times cosine of alpha plus vector b times sine of alpha, closed quantity, cross product with vector p, which is equal to vector b times cosine of alpha minus vector t times sine of alpha. If we differentiate this with respect to arc length s, we find dds of b star is equal to db star ds star times ds star ds, which is equal to negative tau star times vector p star times ds star ds, which is equal to negative quantity tau times cosine of alpha plus kappa times sine alpha, closed quantity, times vector p. Since vector p star equals positive negative vector p, then in consequence of kappa plus tau times cotangent of alpha equals 1 over a, we obtain from the derivative in terms of arc length of b star, which we just stated, that we obtain tau star times ds star ds is equal to plus or minus quantity tau times cosine of alpha plus kappa times sine alpha, closed quantity, equals plus or minus numerator sine alpha over denominator a. From vector x star of s equal to vector x of s plus scalar a times vector p of s, we obtain that vector t star is equal to dx star ds 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 star equals the quantity vector t plus scalar a times vector p dot closed quantity times ds ds star, which is equal to larger outer quantity then beginning a smaller inner quantity, 1 minus a times kappa close the smaller inner quantity times vector t plus a times tau times vector b, and then close the larger outer quantity, then times ds ds star. If we compare the coefficients of vector b in the initial elaboration that we have for t star equals plus or minus quantity vector t times cosine of alpha plus b times sine alpha, and the previous derivation, 1 minus a times kappa and so on and so forth, we obtain that ds star ds is equal to plus or minus numerator a times tau over denominator sine of alpha. If we then insert this ds star over ds relation into the tau star times ds star over ds equals plus or minus quantity tau cosine of alpha plus and so on and so forth, we find the desired result, which is that the product of torsions of curves C and C star given by tau times tau star is equal to the quantity numerator sine squared of alpha over the denominator of a squared, and since alpha and a are constants, then this entire relation is a constant, and we have obtained that the product of their torsions is a constant. And there you have it, folks. That was the end of chapter 2, which is the theory of curves. We just ended it with a few sections. We had involutes, evolutes, Bertrand curves, 4 quick proofs. We returned to our beloved circular helix in the end of the chapter. And yeah, I think the next stream is going to be a review of chapter 2. And then we're going to be kicking it off in chapter 3 with the foundations of tensor calculus. So hope you guys enjoyed, and see you in the next